two very intense sessions. We had a number of presentations, lots of interesting insights from our speakers. Now we have third session, and that is focusing on technology, hardware, software, and systems. We will have 4 speakers that will give us an insight on some more specific aspects related to what it means bringing IoT and Edge together. The first will be Gerald Fritz from TTTech Computertechnik, and he will talk us about smart sensors and systems. Gerald, the floor is yours. If you want to share your screen and present directly from your computer, be our guest.
Good afternoon.
Good afternoon.
You can hear me. Thanks for having me. My name is Gerald Fritz. I'm representing TTTech Auto AG, which is a subsidiary of TTTech Computertechnik AG. Now we'll switch to full screen. Here it goes. For the records, TTTech Auto AG is a subsidiary of TTTech Group, and you can look that up later in the recordings. I quickly skip this. We are more than 2,000 employees around the world, and my specific focus of this talk is to give some insights on the automotive industry and the challenges we are facing with the upcoming future of autonomous mobility. So our experience in commuting from A to B will change in the next years, which will come when we have autonomous cars available dramatically. With this said, the obvious challenge of doing and getting there is complexity and costs. On this slide, the slide is summarized the complexity measured in line of codes of a modern high-end car. So the car software, which you can see on the bottom of this line, there are more than 100 million lines of code compared to a fighter jet in the year 2013, which has roughly 25 million lines of code. So here you can see how complex it is to get from level 3 to more automated driving. So highly automated driving in the future we expect much more million lines of code to come. Why that? So there, and since this is session about sensor and complex systems, currently out of a car with its attached sensors, compared to the American approach of relying heavily on cameras only and having only a few other sensor modalities on board, the European approach on this is having several sorts of LiDAR sensors, several different range of radar sensors, and for sure also camera and ultrasonic sensors. But the point is that the amount of sensors you have in today's car is very, very high, and therefore integrating the complexity of the data which comes from these sensors in terms of collecting these data, performing the sensor fusion and performing the analysis of the data is quite challenging. So as of today, we have in the assisted driving functionalities different functions for all these sensors, which are fused then later on in the control cycle together. And this slide presents just a few mappings of what kind of sensor is particularly necessary to achieve key detection functions for the entire system. For example, a LiDAR in the middle of the blue box on the front, you can make a high precise localization of obstacles in front of the car. So this is just the mapping for these functionalities. Then having these sensor data available, what we are dealing with at TTTech Auto AG is to integrate this, and similar to the robotics domain where you have these obvious action, think, and sense, think, act cycle, you have also in the car integrate the sensors on the left-hand side to the sensor processing, the data fusion, path planning, the control of the car, until you then control the powertrain, the brakes, the steer, the gearbox, the suspension, and several other functions. So having said this, integration platform is also some sort of abstraction layer, which we were talking in the previous session, which assures the interoperability of different subsystems in the car to work together. And this integration software and this integration solution is crucial for having the functionalities available also for future extensions of the functionalities. Where is now the bridge to edge and cloud platforms for the future, coming from a marketing study? Here you see on the left-hand side having the application in blue on the car, integrated with all the sensor information. You also need the connectivity up to the higher level, say edge infrastructure and cloud infrastructure, in order to either update functionalities of the sensors or update functionalities in terms of the autonomous functionality in the car. So as you know, these sensors are not just a data provider for raw data. They are most all of them smart sensors. You heard for sure from the company Mobileye or NVIDIA, which doing some sort of AI number crunching and deep learning. They are providing subsystems where you get object lists out of the sensor itself, and you integrate then these functionalities in the appropriate control functions. So the point is, these sensors have models behind, learned models that are learned on a huge amount of data, and these models will be improved in the future online. They will be enhanced with raw data from each individual car. At least this is the research perspective and the mission, to get better results, to improve based on the current location and on the amount of cars on the road. So that said, you need to tackle the question, how does this data get to a data center where it can be processed all together, not only from one individual car, but from multiple individual cars, say in an entire city. And here, the key competencies which are necessary is, many of them have been already tackled and touched in the discussions previously. You need a connectivity to edge backend, to a cloud backend, and this has to be technology ready at the level where you can rely on these functionalities. Omar from Nokia mentioned this cross-border service continuity, and especially when you're on the highway and you are crossing a border, a virtual border from the cell network provider, you want that your service continues. And this is definitely a very necessary feature, apart from many others, which I highlighted some of them on the right-hand side of this slide. So you have to have these connectivity for future functionalities, for functionalities improvement, and also for the better experience of the user when from commuting from A to B. Last slide. I hope I have been able to give you an impression that the revolution of the automotive industry is also touching very heavily the IoT and the edge and cloud computing domain. We have to make sure that we can provide something vendor independent in the sense of it has to work in entire Europe. The automotive industry is something what Max mentioned in the very beginning of that workshop. We have a global supply chain, we have a global competition. It's not just Europe, it's mainly US, it's mainly China. These are our competitors, but they are all involved in existing supply chains, and it's necessary that Europe brings up a solution on its own that can compete with the global ones.
Thank you very much, Gerald.
Thank you very much.
Thank you. Now I would give the floor to the next speaker. I will take questions at the end because I want all the speakers to have enough time to go through their presentation. And now we have from imec, Ilja, Ocket. He will talk about specialized silicon. Ilja, are you there?
Monique, I think Henrik was first. Maybe she's not here yet.
Well, it's a man, by the way, but then we go with Henrik Madsen. Sorry, Henrik, I just go in the order of the slide, but it's a different order of the agenda. So we have Henrik Madsen from Technical University of Denmark that will talk us about the grid and the edge. So you can share your screen, Henrik, so that you can give the presentation directly from your laptop or computer. We have Henrik Gerald. Yes, I see Gerald. I don't see Henrik. I don't see Henrik. Maybe Henrik did not join us yet.
Yeah, I don't see him in the list as well.
I don't see Ilja either. Nope.
Here, yes, here if you want.
Yeah. Ah, yeah, you're there. Thank you, Ilja. If you can take over the floor, then the floor is yours. I don't know, maybe Henrik had some last minute trouble. I'll give you the floor and you can share the screen so that you can see your presentation.
Okay. Put my video on as well. Hello.
Hi.
Let me just share my screen. I've got the slide here somewhere. Well, actually, I just restarted my computer, so I should find the slides real quick. Yep, here we go. Getting there. All right. If I go in presentation mode, does that still show up? Can you see my screen?
we see your screen, but we see your presentation mode.
Okay, I'll
put it in.
yeah, I'll switch.
The screen.
There we go. The better.
Yes, thank you.
Okay. Good afternoon, everyone. First of all, thanks to the organizers for inviting imec to say a few words on our vision on Edge AI, and more specifically Extreme Edge AI. So I represent the IoT department at imec, where we're very much sensor centric, and we're developing a program on neuromorphic sensing, which happens extremely close to the sensor. In that sense, Extreme Edge AI. I'll run you through kind of mostly a motivation of why we're doing this, what kind of needs we see in industry, and where we think, more specifically, spiky neural networks, which is mostly the topic of this talk, can bring value, and how we're approaching that problem. First of all, we all speak about data deluge being a problem, but in the end, the current deep learning approaches, they need it. You cannot circumvent the need for massive data sets if you want to do deep learning. This is definitely a problem. It doesn't scale very well, and we're, I think, at the point in AI where we have to really reconsider how to have these systems build intelligence, how to scale it in power, in privacy. There's many issues associated with this data deluge. One approach that's where we're kind of playing, trying to develop technology, specific silicon to handle these data close to the edge, is by going to neuromorphic technologies, and then more specifically spiky neural networks. This slide, the guy you see here is Mike Davis from Intel Labs, who is a pioneer and a warrior in getting this technology visibility, and he's basically battling the Jan LeCuns of Facebook and guys like this to really put spiky neural networks on the map. And this slide that he used some months ago now, end of 2019 at MIT, kind of says it all for me. So deep learning is fantastic. It's a great tool. Backpropagation can do a lot and has been used for many applications, but has really fundamental limitations. So this hammer has been helping us to hit a lot of nails in the ground, but many of them just don't work. So here you see a sequence of functions, image classifications and recognition tasks are really well handled by deep learning. Natural language processing, same thing. But becomes difficult if you want these AI, these neural networks to learn with very little data, one-shot, online learning, all of these things, symbolic reasoning. The kind of higher cortical functions are really difficult to realize because of this need for massive data sets. And Mike Davis represents a lab that has a test chip, the Loihi test chip, that allows people to especially investigate algorithms that run on such novel spiky neural network architectures. A very good example, and I've seen automotive pass in the previous talk. Automotive is a clear example where the current approach of making more capable perception systems seems to be hitting a bottleneck. So adding more cameras, more LiDARs, more radars gives you more data, but not necessarily better perception system. And this article in EE Times from a few months ago very nicely describes what is going to happen in the coming years. Adding more sensors will not necessarily bring us better systems. So we need a fundamental breakthrough, and also mentioned in this article are so-called event-based cameras. Also very much an emerging technology, but a possible way out. So event-based cameras, as I'm sure most of you know, are cameras built along principles from biology. So cameras are built using pretty much the processing approaches that your retina uses to do a kind of first level feature extraction. So our eyes don't register every pixel and send all of those pixels to the visual cortex. In fact, there's already some pre-processing being done on the retina, and these things are implemented in hardware these days and being quite successful in showing how it can bring increased performance in latency, power consumption, and so on and so on. So many of these things are happening, and at imec we're both building, let's say, the right sensors, not just cameras, but also radars. We're doing event-based radars now. And you could think of, let's say, expanding this approach to even the LiDARs and other sensors, and even in other contexts. So this just to set the scene a bit. Robotics for us is important. So we have a lot of programs at imec around Industry 4.0, mobility, automotive, etc. And in robotics in general, you see a lot of emerging use cases that will require better perception systems, not just for performance, but for safety. And like I said to Dave, making better perception system often means to throw more sensors at the problem and compute at the problem and hope our current AI approaches will do the job. But again, we're really reaching a bottleneck there. So what do we do at imec? What do I call neuromorphic sensing? It's kind of the marriage between neuroscience and semiconductor technology, where our approach is to look at modern neuroscience as a source of inspiration, but not necessarily a template. So we're not in the human brain project. We're not in the business of trying to build a biologically realistic brain out of silicon. Our approach is rather to use the principles implemented by the brain and discovered by neuroscience to feed into the kind of architectures that we build in semiconductor technology. And that's not just about the architectures themselves, but especially in the case of spiky neural networks, it's about developing the right algorithms to run on those spiky neural networks and to determine the architecture. So architectures and algorithms for us are basically one thing. So we do work from data, but in the end, it's really how we do the algorithms on those data that will determine which kind of architectures we build in silicon. Artificial intelligence, well, I always refer to the old things. So what is intelligence? And Jeff Hawkins in his book calls intelligence what it feels like to have a cortex. So it's really about what does the architecture and the makeup of biology do to create intelligence. There's a lot of insight being developed now around this thing of cortical columns, micro columns, and not just the form, because this is all about form, but really about the algorithms. What are these neurons telling each other? How are they collectively creating models of the world? How are they using input, and especially also how are they controlling motor functions to control what's coming into the cortex and so on. And these algorithms, people are really discovering them, and there's a lot to learn there and a lot to implement in hardware. A few basic points that always come back is that brains don't just passively absorb information and then do something with it. They actually feed forward more than they take in. So 90% of connections are feedback towards the motor functions in biology. And that's a principle very much underexplored, for example, in robotics. Brains don't use a clock. They use time spikes to compute with. They use very sparse representations, which we start to exploit in hardware and in algorithms. Brains use hierarchies to construct complex concepts. It's not all done in a single shot. And then the purple one is the big one. Brains really don't use backpropagation to learn. So deep learning for me is really a misnomer. It's not really learning. It's just fitting data in the end. Coming to how we approach the problem at imec. So we have, of course, we're very much transistor centric. We're hardware people. But if you're serious about neuromorphic technologies, you have to do the algorithms in lockstep together with the hardware. This is a recent example. This is a chip that we designed, had fabricated at TSMC and tested in the lab. It's a digital chip. That's an important thing that it's a kind of strategic choice not to go to analog spiking neural networks, but rather to do digital implementations for a number of reasons, probably the most important one being that digital technology is very reliable. You don't need to calibrate. There's very good tools to do such design. And industry would be probably more likely to accept a digital technology rather than a kind of exotic analog approach. So that's on the hardware side. On the algorithm side, we kind of take the same approach in a way. So we've found ways to train spiking neural networks with standard deep learning tools. PyTorch, the Facebook tool from Jan LeCun, we're ironically using to prove that spiking neural network algorithms do perform for real world tasks. So our approach is kind of from the right on this picture to the left initially. So we develop algorithms, special types of neurons, connectivity schemes, learning algorithms on known data sets. So MNIST, of course, being the Hello World example, but we go all the way to these days Google Speech data set. ECG is a very important one for IoT group and also biomedical oriented group. Radar, Google Solid, the gesture set we've been using. What we've been able to show is that with the right type of neurons and the right type of training algorithms, you can reach the same kind of accuracy levels as the traditional algorithms, but, and that's the very right-hand column in this slide, which you don't see for all the lines, but you see there FR on the far right. This is for firing rate.
Sorry, Ilja, I need to urge you to hurry up a little bit.
Yep,
because
one more slide after this.
Speakers and yes, time is
sure.
running. So
sure.
1 minute to go.
I will finish in 1 minute. So the firing rate shown in the right-hand column is in the end an indication of how efficient this hardware will run, because less activity in the network is less power consumption. So that's kind of our bottom line. So one more slide. In the end, opening it up again. So at IoT and imec, we don't just look at vehicles, we look at other models being a person's body and so on and so on. And the end goal is to not do all the decision making in the cloud, not even at the edge, but in fact, really close to the sensor and build neural networks that can be integrated together with the sensors. We've done spike neural networks in the hundreds of neurons. We're moving now to the thousands of neurons, looking at scalability and especially also sensor fusion in the context of robotics. So I hope that was 1 minute, Monique. With this, I would like to give you back the floor. Thank you for your attention.
Thanks a lot. Actually, I must say, sometimes it's difficult to stop you because it's so dense and so captivating. At least some of the aspects you touched, especially about the brain's functioning, triggered some further questions.
Connect to me later, and I'll be happy to go deeper.
To now announce the next speaker. Henrik Madsen is now online. Apologies, I have to always switch off because there's some construction works on the street and it's a bit loud now. Henrik Madsen from Technical University of Denmark. Good afternoon, Henrik. Will talk us about the grid and the edge. The floor is yours, and if you want to share your screen, we will see your presentation.
Yes, I'll do that. Thanks a lot. So now you should be able to see my screen. I'm talking about supposed to talk about the energy grids and edge computing. And even though we normally focus very much on embedded systems in hardware and software and so on, here I will mostly focus on how we're using IoT and edge computing technologies in order to facilitate the green transition, to deal with the risk for the climate change and so on. And specifically, I will focus on, thanks to the innovations from Martin Brøndskov, I'll focus on the Danish energy system and Energy Center Denmark, or a smart digital energy hub for the green transition. So the challenge we are facing, just to introduce you to that, is that we want to get rid of the fossil fuel generation, which normally used to balance the energy system between renewables and the energy user. But of course, in the future, we should get rid of this centrally located fossil fuel generation, and we will only have renewables and energy users. So that means we need to have IoT solutions and edge computing and digital solutions in general to enable a flexibility at the consumer level in such a way that the energy system is still balanced and taking advantage of the flexibility which we can unlock on the end user side in the water system, heating system, and cooling system, and so on. So what we do with edge computing, cloud computing, and IoT solutions is to unlock this flexibility and this engine down here. One of the things which is also clear is that many other huge European projects which has tried to unlock the flexibility came to the conclusion that there were no flexibility. But I would claim that this is due to the fact that they didn't focus enough on digitalization, edge computing, IoT, and the total digitalization concepts. And another thing they forgot about is the sector coupling to couple the different energy vectors. That's also a very important aspect. So the space of solution they normally consider is grids and batteries, but I would claim that the optimal solution for the world, for the society, is to unlock the flexibility enabled primarily by IoT and edge computing. So this is just, I'm coming from Denmark, like Martin, and what we have today in Denmark is we have roughly 50% of the electricity is coming from fluctuating renewables or wind power, and in order to deal with that, we are now implementing a lot of these edge computing and IoT solutions. And that's, for instance, a topic of this Flexible Energy Denmark project, which is related to this presentation. This picture just shows that, for instance, in July 2020, sorry for the Danish here, the wind contributed to 53% of the total power consumption in July. And of course, many hours, the production is then higher than 100%, and we really need to be flexible. So we are using IoT and edge computing to link currently distinct energy vectors like heat, power, gas, and so on, and water systems using IoT, edge, fog, cloud computing to balance this large scale problem. And of course, with the goal to be able to reduce the CO2 emission from our energy system. We need to focus on different zoom levels and different computing levels, cloud, fog, edge computing, and IoT, and so on. And this just illustrates, this comes from a report where I was one of the authors for Department of Energy in Washington, where we defined the future energy systems, and we agreed that the use of data, IT, is very, very important, and it has to go hand in hand with the coupling of the energy vectors. So what we have implemented in our energy system is what we call a smart energy operating system. And of course, we wrote a book on this a couple of 3, 4, 5 years ago. But the most important thing here is I will focus on the edge, the lower part here. And here you should realize that what we're doing is we are basically just broadcast prices to the edge, to the intelligent billing, to the intelligent wastewater treatment plant, and so on. On the upper level, by the way, where we have the TSO, a DSO, market operator, we still have conventional energy markets and things like that. But when we go closer to the edge, we need more advanced technologies which can take into account the physics and dynamics and stochasticity at the edge. And that's why we are using this type of solutions. So I'll zoom in on the lower level, but in general, the system is a nested sequence of systems, where we have a hierarchy of stochastic models, and which facilitates optimization and control problems, which we can then solve using computers, of course. And depending on the level, we are using cloud, fog, and edge computing solutions and a lot of IoT installations. One of the things which is very important is we are zooming in on a one-way communication strategy at the edge, at the lower level. The reason is that normal household or end user or supermarket will typically not bid into the market. That's one thing. Another thing is that this construction introduces an extra robustness by design, because since we only broadcast things from the aggregators, from the energy system to the users, and we don't send signal back, then we introduce robustness in the setup. And furthermore, it also gave a more simple setup for the communication and the contracts with the end users. We don't need to have very long contracts like we've heard in some countries, where they need to sign papers on 30 pages in order to deliver flexibility for the energy system. So the low-level controllers, or the controller at the edge, are basically based things like that. We have a low-level, very low-level cloud, you may say, where we control, for instance, a thermostat of a building. And of course, we base this control of a lot of sensors, and I'll come back with one specific example later on. So, and the systems we built them typically into software, but also sometimes in hardware. And this is just one example of a smart house controller we have developed, which can make connection over the GSM or mobile network. So it is pretty flexible. So the case study I will conclude with is a case study where we have used where we've used cloud, fog, and edge-based control of heat pumps in summer houses with a swimming pool. So this is a swimming pool with some nice kids, and what we see today very often in Denmark is that since we have a lot of wind power, and sometimes we have too much wind power, so what happens is we simply turn off the wind turbines. And of course, when we do that, we lose 100% of the renewable energy. And then later on, we don't have wind, and then we use more fossil-based energy, and that's of course stupid. So what we do is we are using the swimming pool as a battery, as a storage of course, hot water or warm water, and then which we heat up when we have a lot of wind power, and then we stop the heating when we don't have wind and solar power. This shows the share of electricity coming from renewables in Denmark around December, 1st of December 2016. And we can see it varies from around almost 0 to nearly 70% during this week. Since it's December, we don't really have that much solar power on our latitude. It's pretty dark around 1st of December in Denmark. So most of it is wind power here. So we have then built sensors which sends sensors to the edge computing facility, which again communicate with the back end, which takes the booking of the summer house, weather forecast, and so on into account. And then it controls the different heaters and the pumps in the summer houses. So this is an example from just one summer house, where we are at the red curve now. And this is an example where we're using CO2-based control. We could also have a control which are optimizing energy efficiency or cost efficiency. We could minimize the cost. But it has been very popular in Denmark to rent out the summer houses and label them as being as green as possible. So this summer house has decided to run with a CO2-based control. So we simply want to minimize the CO2 emission linked to the heating of the summer house. So the lower curve shows the forecast of the CO2 emission in the electricity in this area of Denmark over the next 24 hours. And the upper curve, the blue curve, is the boundaries which are selected from the renters of the summer houses. And we can see 12 noon here, I think it's a Saturday. Then some new renters come into the summer house, and we'll have a different limits on the low temperature. The upper temperature is typically 32 degrees. So what happens here is that our edge-based technologies and IoT solutions start up the heating or plan to start up the heating from around 11 11 in the evening to about 3 a.m. in the morning. And then of course it overheats the water. And after that, we can stop using electricity for many hours, maybe a couple of days, where we may not have wind power. So by that we can really save a lot of CO2. In this case, we save between 10 and 50% CO2 emissions. For other summer houses, it can be between up to 25%. So this is implemented as in a new energy center Denmark, where we couple all these techniques on different levels for unlocking the needed flexibility for real large-scale integration of wind and solar power. As I mentioned in the beginning, we passed 50% fluctuating renewables in Denmark in our power system, and when we came closer to this 50%, we saw a need for digitalization on all levels. So we are using AI solutions, cyber-physical models, and edge-based technologies and so on quite heavily, as illustrated in my talk here. And this is now implemented as in the Energy Center Denmark, which is located next to our TSO. We have one energy power system operator, transmission system operator in Denmark called Energinet, and they are located here in Fredericia, and Center Denmark is placed next to our TSO. And this is the control room of Center Denmark.
Henrik, I have to ask you to hurry up a little bit.
Yes, I'm done almost. So this is our control room where we can zoom in space and time and take actions. And this is basically the edge computing technologies. I think I'll stop here. So if you want to have more information, please, you can call me or send me an email or things like that.
Thank you, Henrik. So I would kindly ask Verena to shoot the first questions for this last session, the poll that we had. I see also comments and discussions going on the chat, which is great. Now, Verena.
Yeah, 1 second, please. We quickly switch the host function. Our colleague will do it immediately.
Okay, great.
So I'm stopping the sharing of my screen, right? Or
yes, please. I was going to ask you if you can share stopping your screen, and then our next speaker and last speaker for this session will be Marc Duranton from SCA that will talk about orchestrating the edge. I suggest that we start with Marc, and we will shoot the polls after the end of the presentation of Marc.
Hello, everybody. So do you see my screen?
Yes, we do see your screen, Marc. Thanks.
Okay, so thank you. So thank you for inviting me to this. So this presentation will not be from CEA, so where I'm working, but from IPEC. So IPEC is a hub for European researcher and industry representative in computing system. Every 2 years, we make what we call a vision, which is typically a prediction for the future or where our community should go. So what I would like to share is a part of the vision that, 2021, so it will be present in 1 year, let's say, that is related to IoT. So clearly, the point is, I want to open the eye and see more on the long-term view about IoT. But before going to the future, the best is to think what happened in the past. So I will start with the web. So first, the web 1.0 was only one-way road. So the content and the presentation were imposed by the service, by the provider. By only adding a thin software layer called WebSocket, we changed the monodirectional web into the web 2.0, where user could put data or could provide data to the server, allowing all sharing data on all the social network. What we also observe now is that there is a less use of a web browser. Instead, we have more and more specialized app for services. So, for example, you have an app if you want to book an hotel room in, I don't know, in one chain of hotel. But what you have also is that you have aggregator that's allowed to select which hotel or which hotel chain is the cheapest according to your criteria. So what is the best service? And we even see now the aggregator of aggregator that's allowed to select between this aggregator. So it's becoming really to be a mess with an overflow of information, of choices and things like that. On what industry? So if you want to provide some function, and what user wants is services. I want to book a room in an hotel. I'm not having to download or to use hundreds of various applications that are more or less doing similar services. So the other point is we are going to more natural and contextual interfaces. So more and more we move from the PC with the screen and the keyboard to the smartphone where keyboard is no more present, it's touch interface, but even with other interface with the real world, like voice, like understanding the vision or the context. So what is also going is that the edge, so the terminal, need to be more and more aware of the environment and adapt its input more and more to the situation. So in IoT, which is the link also with the real world, we have also the links with heterogeneity of the physical world, of the physical quantities that we want to measure and to transmit, that lead to also a large heterogeneity of IoT devices for various application or industry domain. What we could see also is that in the past, and it's slowly changing, is very vertical. So you have a set of applications, software, platforms that are for smart home, for smart shopping, for smart healthcare. And we know here that the added value is when you go cross these silos. So combining shopping with the smart city and things like that, it's really where the value will be. So we need to move to more horizontal platform that could cover all domain, and of course we'll have to cope with the complexity and with the diversity of the sensor and the software stack. One other constatation that we have is that programs are not anymore localized in a PC or in your smartphone. They are executed in the continuum. So parts are done on the smart, on the edge, and the data are consolidated into a smartphone or to a local server, and after they could go to the cloud or to a diversity of devices. So we see now that it's more multiple distributed function that could be seen as a services gluing together. That's the new program structure. We even see this at the programming level. So the success of Python is not because it's a nice language, because it's a glue between more specialized library. So we go towards a digital continuum where you have smart sensor on IoT, generated data to a platform, smart network and services that are created with big data that are analyzed on the HPC on the cloud and could feed back to the physical world with the CPS system. So for example, driving a factory and things like that. So what is good now is that people are more and more aware that we need to break these silos between application and between, let's say, IoT, communication, big data and things like that. And there is an initiative called a Transcontinuum initiative that try to have all this community to work together. And today, this initiative involves UTP for HPC, for the HPC domain, EXO for the security domain, BDVA for the big data value association, 5G, Ilja, EU Mats, CLAIRE for IE, on IPIC, and more to come. What also people see and also is that a non-European trends, or let's say the GAFA and Bytics, is to move all the data back to the cloud so that they could master and control of the data. Here in Europe, we say that we should process information as soon as we we can, and typically we need to transform data, which is the raw material, like the fuel, like the natural petrol, into information, which is really useful, and this as soon as possible. So possibly in the edge, so for a reason of latency, on privacy, on lower power consumption. So what we see now is that we will have all these elements that need to work together in a plug and play with self-management and orchestrating all these elements together with virtually no human intervention. So with all the concept that you could see here with self-discovery, self-configuration, self-healing, and things like that, that are important things. So what we see is that we have all the pieces of the puzzle, and we need to assemble them into a coherent picture. And to overcome all the challenge, so the fragmentation on the vertically oriented closed system, so the heterogeneity and interoperability, and also taking into account the non-functional requirement like energy, latency, and things like that. So if you want to go up to cyber physical system, like controlling a factory, when you offer a service, you need to tell to the user, okay, I will perform my task in X milliseconds, or I will use it in best effort. So perhaps here the orchestrator, depending on the condition, could choose one or the other services, depending on the overall task it has to assemble in this orchestration things. Scalability, dynamicity are also very important because of this complexity and increasing size of all devices working together. But here also, the web technology shows that we could manage billions of devices together with plug and play and things like that. And of course, privacy, but I don't have time to dig too much into this. So clearly the idea here is creating the next web, intertwining cyber and physical world for industrial and personal use and build on top of existing technology. So it's where we come to this idea where you have the physical world with physical quantities, with sensor and actuator, and it's here where we have this orchestrator that we call guardian angel. Why we call it guardian angel? Because it's a barrier or the interface between the physical world and the external world. And it also take care of your private and very company confidential data, knowing which one it could share to whom and which one it's need to protect. So it's also this guardian angel that will have to orchestrate all the functionality that will be outside with this dynamic construction of application for distributed and remote services. So taking into account all the non-functional requirements. So on the technical detail, we think that it should be built on a trustable distributed meta-level operating system. So Max Lenke this morning talked about this idea. So what we call trusted computing base, and of course should be running on edge hardware. So in view of time, I will not have to dig too much into the technical detail of how it works, but clearly it's composed of a lot of different elements, like natural interface to give order or give prescription to this orchestrator, so using artificial intelligence. In and outbound data protection, so filtering data, filtering what is private, what is company confidential, what could be shared, based on the web, so basically on the actual resources on the web using REST API, for example, and building on the trusted computing base. So in the slide, you will see these two next slide, which is more detail on how we think it could be done with the existing technologies. But for finishing, I would like to give you one idea. We think it could be nice to have a moonshot project trying to define these cross-domain activities so that we could try to construct this next generation web using IoT devices, interacting with the real world and with the cyber world. And here we need to have synergy between a lot of domains. So working on interoperability, and we think that here we need a contract-based approach. And in this contract, we need to expose a non-functional property. So security, privacy, safety with controlling in and outbound data. Edge processing, and also how you could federate your local resources for your system. So of course, having this orchestrator on trusted computing base, we think it could be open source so that it could be reused. So we have also idea on the business model behind it, and also being open source is that it could be inspected and be more secure with a lot of people inspecting it. So also linked to EI for natural interfaces and context aware. We think about a legacy also with containerization, supervisor for non-trusted legacy part, and also the hardware side. So this could be run on a hardware platform, on an heterogeneous hardware platform.
Thank you very much.
Presentation. I would like just to see if you want more idea about this. We make a comic book that you could download, and this was done for the anniversary of the web, and where we expose in a most funny way all this idea of Guardian Angel. So that was the end of my presentation.
Thank you very much, Marc. Thanks a lot for this dense and inspiring presentation. We all need guardian angels, especially in those very special and turbulent days. Let me thanks once again all the speakers. I would like to Jean-Baptiste, if we can go ahead with the poll. So we have a question that is what is the way ahead? Nope, that's not the one. We want to have a question. The first question of session 3. Yes. So this session was very much focused. It was quite heterogeneous, the presentations we have seen, but there's a lot of commonalities. And here I see that there is a mistake in the poll, because twice we have smart devices. So what are the major complexity factors? Essentially, smart sensors, smart devices. Here, the third item should have been smart infrastructures. I think depending on the application and viewpoint, it's very much the case. We are indeed seeing that there are physical constraints, physical boundaries that need to be challenged more and more. We have heard the presentation from Ilja about, how to go down to specialized materials that can be more versatile and more adequate for the kind of edge computing scenarios. What I would like also to reiterate, if you allow me, is a very important point. We've been discussing a lot about technologies, about applications, about needs of our society, but we have also heard a lot about energy. Especially in this last session, it's clear that we need to be aware of what the technologies cost to our planet and to our environment. And I think there are several ways in which also edge computing can directly contribute to, by decentralizing and minimizing also the data that needs to be transmitted and transported, energy consumption. Of course, there's other kinds of challenges, as we all know. But I think there's a lot of very inspiring points that we touched today. Now, I would like to give more time to our speakers, but we have we are a bit late. Now there's gonna be some informal chat in the breakout rooms available, and I would really like to give space to that, because so for instance, Marc now announced their intention to launch a moonshot project. Some of the questions emerged in the chat, and I see questions for Ilja. I see comments to the presentations. So I wish, I really wish you a productive exchange of information, because I think in the one-to-many modality, we risk to lose the audience. I see that we are still 100 people, and I would really like to give this opportunity to discuss and talk and liaise. We will reconvene at 2:25, so the break is 10 minutes, with a session dedicated to on enabling technologies that will be moderated by Ovidiu Vermesen, Chief Scientist at SINTEF. And we'll have other speaker following up before the closing that is planned at around 4 o'clock. On my side, I unfortunately have to leave you, so I would like to thank you all for your attention, and please stay tuned on the NG IoT channels, because more information, the slides, the materials, a report will be made available. So thanks a lot, and have a good rest of the afternoon.